The quantum world, it's a place that defies reason, a place where objects exist in multiple places at once, where particles flip between states like characters in a dream, where communication seems to happen instantly across the vast emptiness of space. This is the strange universe of quantum mechanics, and yet our world, the everyday world you and I live in, feel nothing like it. Here things are solid, predictable, governed by the simple rules of cause and effect. But here is the great cosmic riddle. This classical word emerges from the quantum, so where does the transformation happen? At what size does really stop being quantum and start becoming classical? And how does gravity, the most familiar force of all, fit into this strange puzzle? Gravity feels crisp, definite, smooth. It sculpts planets, stars, and galaxies, but space-time itself is woven at scales far smaller than quantum physics. So, at what point does space-time itself become quantum? Today we dive into one of the biggest mysteries in all of science, the transition between the quantum and the classical, and how gravity, the force that rules the cosmos, might secretly be quantum as its core. The quest to shrink gravity, our story begins over 2 centuries ago with one of the most elegant experiments in physics, the torsion pendulum. The genius behind the idea was Johann Michael, an often forgotten hero of science. He was the man who first imagined dark stars that light could not escape, the earliest vision of what we now call black holes. But Michael had another vision: to measure the weakness of all forces, gravity between objects small enough to fit in your hands. Imagine suspending a delicate rod by the thinnest of wires at each end. Attach a small metal bob. Now bring larger masses close to them. Gravity pulls the small balls towards the large ones, twisting the wire ever so slightly. By measuring the twist, you measure the gravitational force itself. This was revolutionary. For the first time, humans could try to weight the earth. Sadly, Michael died before he could finish. But this close friend, Henry Cavendish, carried the idea forward in 1798. Cavendish built the device and achieved the impossible. He measured the gravitational constant big G to an accuracy so extraordinary that even today, more than 200 years later, we have only improved it by a single decimal place. Cavendish called it weighting the earth, and indeed, with big G in hand, the mass of the entire planet could finally be calculated. And you know that the mass of Earth is 6 multiplied by 10 raised to power 24 kg. But science never stands still. Modern physicists asked, what happens if we shrink? Cavendish experiment, not with huge lead balls but with tiny golden spheres barely a few millimeters across, 1,000 times lighter than Cavendish masses. These delicate beads are suspended by threads thinner than a human hair. They are placed inside vacuum chambers, shielded from every electrical charge, protected from every stray vibration. And here is the challenge. At this tiny scale, gravity's pull is so weak it's easily drowned out by other forces: electromagnetism, van der Waals interactions, even the Casimir effect. Yet, with breathtaking precision, physicists in Vienna pulled it off. They managed to detect the gravitational attraction between two gold spheres, each less than a tenth of a gram. How sensitive was this? The gravitational force they measured was no stronger than the pull of a graduate student standing 3 meters away. Even the rumble of a tram passing outside the lab could interfere. That's why the experiment had to be performed between midnight and 5 a.m. during the quiet Christmas season, with students asked to sit motionless in the lab. And still they measured gravity, tiny, faint, whispering, but real. The results: Gravity behaved exactly as Newton predicted even at this near quantum scale, but how far can we push it? Physicists dream of going smaller, much smaller, down to the Planck mass 10,000 times lighter than those gold spheres, and perhaps one day all the way down to the scale of atoms themselves. At that point, if gravity behaves differently, we might finally glimpse its quantum nature. The quest to enlarge quantum. If one path shrinks gravity towards the quantum, the other path is to make quantum effects big. The most iconic of all quantum phenomena is entanglement. Two particles linked by an invisible thread, their fates bound together no matter the distance. But enlargement is fragile. The larger the system, the faster it dissolves into classical behavior, a process we call decoherence. And yet, physicists found a way to fight back through the strange art of optomechanics. Imagine a laser bouncing between two mirrors. The photons strike the mirrors, nudging them ever so slightly. The mirrors move, changing the cavity. The cavity shifts, changing the photons. This creates a feedback loop. Done carefully enough, the light and the mirrors become quantum entangled. In 2010, this was achieved with a tiny silica membrane, and in 2011, two mirrors were entangled not just with light but with each other. Think about that. Two microscopic objects, visible, tangible, linked by quantum entanglement. The boundary between the quantum and the classical began to blur. But physicists want to go further, much further. What if we scaled this up to innermost proportions? Well, good news. We already have. It's called LIGO, the Laser Interferometer Gravitational Wave Observatory. A machine so precise it can detect distortions in space-time smaller than a proton's width. LIGO's mirrors weigh 40 kilograms each. They are kilometers apart, and in principle, they could be used to detect entanglement between these massive objects if that's possible. We have been witnessing quantum entanglement on a truly microscopic scale. The work has begun in 2024. Physicists reanalyzed LIGO's data with new tools to filter out tricky non-Markovian noise that mimics entanglement. So far, no success, but we are close. Imagine it detecting entanglement between objects heavy enough to hold in your hands. That would change everything. The holy grail, quantum gravity. And now we come to the dream, the holy grail of physics, to detect entanglement caused by gravity itself. If gravity can entangle two objects, then gravity must be quantum. That would mean space-time. The very fabric of the cosmos is woven of quantum threads. How might we prove this? One idea: suspend tiny elements, place them into quantum suspensions, and let their gravitational tug entangle them. Another: use oscillating pendulums, watching for collections that only gravity could explain or spin. Dependent superpositions that create slightly different gravitational fields. Each idea is bold, each one demands technology we are only just beginning to build, but none of them are impossible. For the first time in history, we may be within reach of testing whether gravity itself is quantum, not with cosmic colliders, but with tabletop experiments. Physics has always been about chasing whispers, from Newton's apple to Cavendish lead ball swinging on wires to lasers, diamonds, and entangled mirrors across kilometers. Every step has brought us closer to answering the most profound of questions: where does the quantum end and the classical begin? And is gravity the force that holds the cosmos together, sacredly quantum at here? One day soon, in the quest of a laboratory, on a silent thread, of light, we may hear space-time whispering its answer. Physics is not just science. Physics is the poetry of the universe written in reality itself. It exists in multiple places at once, where particles flip between states like characters in a dream, where communication seems to happen instantly across the vast emptiness of space. This is the strange universe of quantum mechanics, and yet our world, the everyday world you and I live in, feels nothing like it. Here things are solid, predictable, governed by the simple rules of cause and effect. But here is the great cosmic riddle. The classical word emerges from the quantum. So, where does the transformation happen? At what size does reality stop being quantum and start becoming classical? And how does gravity, the most familiar force of all, fit into this strange puzzle? Gravity feels crisp, definite, smooth. It sculpts planets, stars, and galaxies, but space-time itself is woven at scales far smaller than quantum physics. So, at what point does space-time itself become quantum? Today, we dive into one of the biggest mysteries in all of sciences: the transition between the quantum and the classical, and how gravity, the force that rules the cosmos, might secretly be quantum at its core. The quest to shrink gravity. Our story begins over 2 centuries ago. One of the most experiment in physics